Lab number 6 is entitled Designing a Stabilizer for a Differentiator Circuit. Stability is considered by many to be one of the most common problems in electronics. In this lab, we're going to take a look at what's called a differentiator circuit. This is a circuit whose output is a derivative of the input times a scalar. This particular circuit suffers from near instability, which results in a lot of overshoot and ringing in the output. Your design task for this lab is to modify the differentiator circuit so that you can eliminate this overshoot and ringing, but still maintain the functionality of a differentiator. Well, the techniques you looked at in class are built around using the open loop curve of an op-amp, the response of what's called the beta network. As we'll see in the next lab, it's very difficult to measure the open loop curve versus frequency. So we can play a little trick or a game, and that is to use a closed loop circuit and work some of the numbers backwards, figure out the resulting curves. Now, we'd analyzed this circuit in class and found that the low frequency gain was equal to 1 plus R2 over R1, but also the term 1 over beta was equal to the same expression for the non-inverting amplifier. In other words, you could write that as 1 plus R2 over R1 or R1 plus R2 over R1. And then in the class, we looked at turning this into a schematic so we could think about designing, in this case redesigning, to get things to work. Now, the corner frequency of this circuit's at the gain bandwidth product divided by 1 over beta. And again, 1 over beta in this particular case is the same as the low frequency gain. We'll get a plot versus frequency. That's flat, and when we hit the corner frequency, we'll be down 3 dB. And as we mentioned in class, as the frequency increases beyond that corner, we begin to follow the open loop curve times the scalar. In this particular case, the scalar turns out to be just 1. The differentiator circuit shown in figure 2 consists of a capacitor and a resistor in a feedback path. If you apply a voltage V in, all that voltage is across the capacitor because the op-amp's input terminals has a very low potential with feedback. And that creates a current, and that current flows up into this resistor and creates a drop. Okay, the current is related to the derivative of the voltage across the capacitor, but that is our input voltage. That current then gets multiplied by R2, and their output voltage then is the negative of that plus 0. And so the output is a minus R2C1 derivative of Vn. Now, our technique in class was to turn algebraic expression into an equivalent circuit so that we could think about manipulating the circuit for improving stability. If we go back and look at this schematic, technique we talked about with beta networks was to, let's erase these things that are here, is to set this equal to 0, cut the op-amp out, and put an independent source here. And then the response with the opposite polarity of the op-amp divided by now this independent source has the same expression as beta. So in this case, this is our beta circuit, and we've got the impedance here divided by the sum of the two. In other words, Z1 over Z1 plus Z2. So how this circuit's behaving, we can then look and see if that's the cause of our stability problem, and it usually is, and then how would you fix it or change it. Let's sketch what this looks like versus frequency. When the frequency is low enough, this capacitor becomes an open circuit, and no current flows. This node voltage is the same as this node voltage, so we have a gain of 1, or 0 dB, at low frequencies. As the frequency goes up, this becomes a short circuit, and the output goes to 0, but it's going to go as 1 power of s, so that means we're going to have a rolling down of 20 dB per decade once we hit some corner frequency. And so we could figure out where that corner frequency is if you think about this being Z1 over Z1 plus Z2. But Z2 in this case is just a resistor. The capacitor is in Z1. This is just 1 over SC, so we kind of know what that's doing. And then this denominator is really the series combination of these two. Now, where that has a 0, that's where beta would have a pole. And that's what we're looking for here. We see a pole in the response because the slope has decreased by 20 dB per decade. If you form our one capacitor technique, here's the terminals of our impedance. We're going to look back from the capacitor with the terminals shorted. So what you see looking back here is just this resistor R2. So the pole is at 1 over 2 pi R2C1. If you sketch 1 over beta on the open loop curve, again we're going to measure this by measuring a closed loop circuit and literally get the this part of the curve, and then we can just extend it past it, find roughly the open loop curve. Take the reciprocal of the previous expression, it's going to run into this open loop curve where the red dot is, and the rate of closure in this particular case is the slope of 1 over beta, which is 20 dB per decade, minus the slope of ADM at the point of intersection. And that's 40 dB per decade. And we've seen in class that that causes very poor phase margin and sometimes total instability. But you'll see that in our particular case in lab that we're kind of sitting with poles on the j omega axis. We're going to get a lot of overshoot and ringing, almost like an oscillator. So before you come to lab, I'd like you to take and run this circuit. This is a simulation of that differentiator with a particular input. I'll let you figure out what that is. And the model that we're using for the op-amp is going to be the full macro model that we've been talking about in class, and it's in the 402 library. You get to see the real effect, the total model of the op-amp. Your design task is to change this rate of closure such that it's less than 40 dB per decade. So you got to think about what do you have to do to this beta curve in terms of its graphical representation, and what would that correspond to in terms of poles and zeros in the beta network, and then correspondingly how does that go back into the original circuit. We'd like to keep this frequency F1 the same because this gives us the property of a differentiator in this frequency range. Differentiator is just S times a scalar, and so that's equivalent of a j omega, so it's a term that has a 20 dB per decade slope. But it's when it gets to this frequency where we got a problem, so can you figure out how to fix that out? So do a spice simulation of your improved circuit and bring that to lab. Make 2 copies of your pre-lab report and submit one of those to the lab instructor, and he'll use that in the grading of your lab. Maybe bring your spice files with you, and you can also then update them with your actual values of components. This is lab number 6, designing a stabilizer for a differentiator circuit.